huge thanks to the organizers for putting our favorite events here in Corfu together, and for giving me the opportunity to be part of this special memorial edition of the Corfu meeting. I didn't have the opportunity to meet John personally, unfortunately, but his work did influence me quite a lot. For example, because I don't think I ever gave a talk that didn't have fuzzy in the title. So today I will tell you something about our work here with Harold, following a piece of his previous work. Now, I realize the schedule of this meeting is very tight, and I will not blame anyone if some of the things that I say will blend eventually with other ideas you will have heard over this past week. But it would be really great if you could take at least these three messages with you home. So there is an interesting and at least a certain extent new way how to describe things that are happening on fuzzy spaces. This description works in position space and uses the coherent states we all know and love, but not only as the basis of the auxiliary Hilbert space that's used to define the fuzzy space, but also as a basis of functions and operators on these fuzzy functions. And when you look through this new prism onto fuzzy scalar field theory, there are some new things and new perspectives that pop out. So let me begin by getting us all on the same page, even though most of the things that I will show you in this introduction you have already seen in the earlier talks today. And I will talk about the fuzzy sphere, but everything I say can be generalized to more complicated fuzzy spaces. Now, the regular sphere can be described by the algebra of functions on the sphere, which is generated by these three coordinate functions. And then the fuzzy sphere is formulated by a deformation of these relations. Now, you realize that these are basically the definitions of the generators of SU2. So you realize X's as the generators of SU2 in n-dimensional representation. And you can see that as you take n larger and larger, then you recover the expressions for the original sphere. Now, the fuzzy sphere is defined as whatever this algebra generated by this axis is algebra of functions on, and these axes generate algebra of Hermitian matrices, so fuzzy functions are Hermitian matrices. N times n Hermitian matrices can be expanded like this into the basis of polarization tensors, which work the same way as the spherical harmonics do. There is just a cutoff on the largest would-be angular momentum in this expansion. And let me state there explicitly that the space of such matrices is n-squared dimensional. So now when you want to do physics on the fuzzy sphere, you take your favorite physical theory, for example, Euclidean scalar field theory. You take the commutative version, you find your commutative to non-commutative dictionary, and you translate. As I said, fields become matrices, space-time integral becomes a trace of this matrix, derivatives become generators with the commutators with generators of the rotations, and most importantly, the path integral over functions becomes now well-defined finite dimensional integral over the space of matrices. And you define your theory as through these functional correlation functions, and you let Feynman diagrams do their magic. These are some very nice overviews of that. And for what I want to say, the most important result is the UVRR mixing, which there's a lot to say about. But at the end of the day, at the very end, what happens is that when you write one loop effective action for the theory, you take the large n, i.e. the commutative limit. The underlying sphere forgets about its fuzzy origin, but the one with effective action remembers it came as a limit of fuzzy action. There's this term that doesn't vanish in the commutative limit. It's a mildly non-local term, which cannot be cancelled by any local counter term and leads to a non-local theory that is not renormalizable. Okay, so after this introduction, let me tell you what I mean by the cryptic string modes. And the basis of the auxiliary space can be naturally taken as the, you can call it the spin basis of the state generated from the highest weight state. However, as we already heard today, you can do something different, and you can define the coherent states, which you get acting on the highest weight state by a matrix that rotates the north pole of the sphere onto a given point x. Using this formula, you get one state x for every point on the now usual regular round sphere. And the set of all these states is called the coherent states. Now, so there's a vector x for every point x on the sphere, but I want to emphasize that these x's are elements of the auxiliary Hilbert space H, and they're not functions on the fuzzy sphere. They are not matrices, they are vectors. And you can think of them as non-commutative analogs of the point x. So actually there is some point in the pointless geometry. And you can forget about the sphere altogether, and there's a way how you can define the coherent states without the reference to any underlying classical space, just starting from the matrices. And there's a huge body of literature how this is done, and I refer you to Harold's recent paper and references there. What's going to be important for what I want to say is that the set of coherent states is complete, meaning that any vector in H can be expressed as a linear combination of x's, and it's even an overcomplete set of states, because obviously the dimension of H is n, and there are much more coherent states than n. Now, they have a non-zero overlap, so even though x and y corresponds to different points, they're not completely different vector, and this overlap vanishes only in the Lagrangian limit. And you can use coherent states to quantize regular functions on the sphere, or dequantize, meaning you can map matrices on the functions. Yeah, this is the symbol that we've heard about earlier today. Now, what this map does is it maps the polarization tensors onto the spherical harmonics and vice versa, but it does it after normalization. Now, this might look a little technical at the moment, but when you do the calculation, something interesting already starts showing up. You see that this expression in the Lagrangian limit behaves very differently for L smaller than the square root of n and L larger than the square root of n. For L smaller than the square root of n, this is essentially a constant, and this map these two maps are basically inverse of each other, and everything works nicely. For greater L, this C starts to do some funny things, and it is already not that simple, and interpreting straightforwardly these two, or naively interpreting these two maps leads to something does not completely fine. So this is already first clue that something interesting is happening at the scale square root of n. So now coming to the fuzzy functions, obviously this is quantum mechanics. You can express matrices in the basis of the spin states. However, since the coherent states form also a basis in the space of matrices, you can do this, basically the same thing, and express the matrix as a superposition of objects like this. And as do objects Nn form bases in the space of matrices, so do the objects X, Y. So you take these objects, you give them a name, string modes, and you have basically constructed an interesting basis of n times n matrices in terms of the coherent states. Now come what I consider to be two most important slides of my presentation. So if you happen to have just a little bit more capacity than the 3 bullet points I showed you in the beginning, this is probably a good time to use it. Obviously, there's much more information in function of 2 variables than there is in a single Hermitian matrix. So it seems that this is little too much, isn't it? But actually, you can show that anything that happens in function phi that changes faster than Fourier mode with momentum square root of n gets washed out. Any modes of phi xy greater than square root of n simply do not contribute to the matrix. And you can restrict yourself onto functions phi that are very mildly changing. So there are basically no oscillations in phi xy that represent the matrix M, which is different from the symbol phi x that I showed you a couple of slides before. The reason for this is that the coherent states are localized on a finite, they are spread over a finite area of the fuzzy sphere proportional to 1 over n. Therefore, whatever happens with this function over that area gets averaged out and doesn't contribute. So we got a function representation of the matrix that is very nicely UV behaved. It's very mildly changing. However, the price we had to pay is that we needed to switch from the local basis to this non-local basis of string modes. Regarding the string modes, you can obviously ask a very natural question: what happens if you take x and y to be so close to each other that from the fuzzy sphere point of view, there should be no distinction between the 2 points, i.e. the difference is smaller than this? Then you can show that such a string mode corresponds to a localized wave packet on a regular sphere that's localized somewhere in the vicinity of points x and y, and that has momentum proportional to n times the distance between the 2 points. So these short string modes represent the classical regime of the theory with a cutoff on momentum of square root of n. And particularly when you take x equal to y, you get a wave packet with 0 momentum. You get whatever is the maximally localized object you can get respecting the fuzziness of the sphere. So you get a fuzzy version of the delta function. And matrices that are represented with functions like this are thought to be are best to be thought about as local functions. Those are objects that become the standard commutative functions on the sphere in the commutative limit. On the other side of the spectrum, when x and y are far from each other, then this has no classical analog, and this truly is a non-commutative regime of the theory leading to non-commutative effects. Okay, so now we want to do field theory. We need operators on the functions, and the most important things for us are going to be the Laplacian and the propagator. Now, as Harold showed you yesterday, simply by construction is not too difficult to see. these xy string modes are eigenfunctions of the Laplacian with eigenvalue proportional to x minus y. So this is where the string string name comes from. Yeah, the energy of the xy mode is not unlike the energy of a string stretching from x to y. And now you can play the same game. You can try to express operators, which are at the end of the day n squared times n squared matrix, in this new basis of string modes, similarly as we did a couple of slides ago. And now again, you can try to see what kind of functions you can get here. You can try to force the operator to have this local expression, but then the local functions are very, very oscillating, and something that's better behaved is this diagonal but non-local expression. As Harold didn't show you yesterday, this expression is very useful when you want to compute the operator traces. Yes, because it just if you are able to compute this matrix element, then operator trace is just a regular integral on the regular sphere, which students learn to do in their undergraduate courses. So, and Harold showed you some of the very interesting results of similar calculations in much more complicated theories than what I'm telling you about, what I'm going to tell you about that later. So, but I want to concentrate on the propagator. So propagator is diagonal in the xy modes because those are the eigenfunctions of that operator. And now again, doing some tedious algebra, you can show what are the local and the diagonal elements of functions of the Laplacian. And after some work, you can massage this formula in the large n limit into something like this. Now, you don't need really to follow this too much. I just wanted to show you that we know what we're doing, because when you calculate the trace of the propagator using the formula I have shown you, you get the very same result you do when you calculate it using the usual formula. So things are working out quite fine. So let me get to the field theory. Now, when you write the propagator connects two string modes. So when you do the Feynman diagram in this formalism, in this basis, the propagator connects xy with some other string mode xy. So it needs two lines and leads to ribbon diagrams that we are quite used to from matrix models, which are at the end of the day related to fuzzy field theory. So that is not too surprising. What is interesting that in the large n limit, the x and y indices now, let's call them, are preserved. In a very similar fashion as with the matrix model, the indices were also preserved along the lines of the ribbon graph. However, these were the matrix indices in the spin basis, and now these are the matrix indices in the string modes basis. And as you might be familiar with, taking care of this kind of matrix model in the spin basis ij is notoriously difficult because of the kinetic term. What happens here is that the string modes diagonalize the kinetic term, so nothing changes along the propagator, and the string mode that started at the beginning of the propagator is the same string mode as is at the end of the propagator. Now, vertex is basically the same story. Again, in the large n limit, I stress this. This is the large n limit is crucial for this to be true, again produces a vertex that where the indices, which are now labeled by a point on the regular sphere, are conserved. So string modes do magic because they at the same moment diagonalize the kinetic term, so we can use nice propagators. However, they keep quite simple structure of the kinetic term, sorry, of the vertex. And they do this in position space. So the calculations are similar to what happens in regular field theories. However, there is no issue with singularities because we're on a fuzzy space, and there's, from technical point of view, there's a cutoff, there's a natural cutoff, and from conceptual point of view, simply there is nothing as points close to each other, coincident points on fuzzy space. So we can work in position space, but we do not need to worry about divergences at all. So this is how the vertex looks in the string mode formalism, and now you do your Feynman diagram calculation. Yeah, for the one loop, you can connect either these two legs or these two legs, and this leads to two very different diagrams. The interesting thing is that the free variable that you integrate over now is an intermediate point on the sphere. But what I want to stress here is that the planar diagram connects mode xy with mode xy. However, here in the non-planar diagram, when you follow the point along the loop, you end up with local string mode xx connected with a non-local string mode at the end of this diagram located at yy. So now you can calculate the one loop effective action for the and then take the commutative limit. So calculate the one loop effective action for the local field phi x, and what you obtain is this, which can be shown to give the same result as you got in the momentum basis calculation. However, the calculations are not that, are little more transparent, and there's quite a clear interpretation. This term leads to the same effect as this term that can be shown. However, here you can see what happens. Yeah, the planar diagram leads to the regular mass normalization, but the non-planar diagram leads to a non-local term that couples field at position x with field at position y, and it couples them through a long non-local string mode running in the loop of this non-planar diagram. And what's the biggest advantage of this approach is that you can straightforwardly go beyond one loop, which is next to impossible, or you would need to gather too many PhD students to do the calculations in the standard momentum basis representation. But here it's quite straightforward to write diagrams like this. And what is most this leads to some usual terms, but then you can write diagrams that are like this, which lead again to those XX, YY contributions that contribute to the part of the effective action that leads to UVR mixing. And now you can show that this particular diagram is not that problematic. It's less non-local. It produces a term that's less non-local than this thing here. But this diagram produces something that's even more non-local than the one-loop contribution, and this diagram produces something that's even more non-local than this two-loop, and therefore more non-local than the one-loop contribution. So you can see that iteration of this process leads to more and more non-local contributions into the effective action, which is basically the idea you get when you do the momentum basis and you get the non-planar loops on loops, and you get the UVR mixing. However, here it is interpreted straightforwardly as exchange of the long non-local string modes that are in the square root of n to n regime of the fuzzy field theory. And with that, I flash for you again the 3 bullet points I would like you to remember. Most importantly, that there's a different way you can try to understand things happening on the fuzzy sphere. And with that, I thank you for your attention. Thank you very much, Juraj. You were in perfect timing. So it's time for questions or comments. First of all, please.
I'm just trying to understand the interpretation of the propagator that you showed. If you could go back to the transparency where it was written. Yes,
Yeah.
this one. So how do I interpret that quantity? The delta functions tell me x1 must be x2, y1 must be y2.
Yeah.
So do I interpret it as propagation in the vertical direction or the horizontal direction?
Oh, no, in the horizontal direction. I'm sorry. It's just a ribbon graph of as in the matrix models. This is probably the best thing to. Or the fat graph. You just made the legs of the diagram fat. So you remember that you need when you do the contraction, you couple this part of this leg with the outgoing arrow with the incoming arrow, and this incoming arrow with this outgoing arrow, not the other way around.
Okay.
So to answer your question, you interpret this horizontally as one line in the diagram.
Thanks.
It would be interesting to see what happens if you try to do this with the disk, with the fuzzy disk. Of course, I'm asking this question.
Okay.
Because there you have exactly the same basis, what you call the string basis, but there is a boundary there. So this would be a field theory with a boundary.
Okay.
So it would be, well,
yeah,
it would be an interesting thing to see how the boundary would affect these propagators, these things. So.
It looks like Harold has something to say about that. The thing that comes to my mind is that you would see how because for finite n the disk doesn't have a boundary. It just a boundary appears in the large n limit. So you would need to see how the coherent states work around the boundary in the large n limit. But perhaps Harold has something better.
Yeah. So the point is, all of these results are completely generic. They will work for any non-commutative space as long as it is non-degenerate, so as long as it comes from a symplectic space. And as long as you can realize the Laplacian as a double commutator with some generators. That's really what enters.
But that's what you can do.
Exactly. And then, so it doesn't have to be constant non-commutative. It can be anything. It's always the same effective action. It's really, all of these things behave universally in the ultraviolet. That's the nice thing about it.
Yeah.
So you can do it immediately.
Some issues with the mixing with the it's a comment, of course.
Yeah, but I cannot say from top of my head what the boundary is going to lead to.
Exactly. So the boundary will be something new. Yeah, that's true. Yeah. But you can do it.
But that's a great point.
Thank you for these questions. There's time for one further question. Let's check whether we have some comments or questions from the online community. Okay, so thank you, Juraj.
Thank you.
And we come to the second speaker, that is Sachindeo Vaidya. Hello.
Hello.
You have 25 minutes, and then there is 5 minutes questions time.
Can you hear me and can you see my screen?
Yes. So Vaidya will speak about new results in SUN gauge matrix models. Please.
Okay. Thank you very much. I'd like to thank the organizers for inviting me to Corfu 2021. As you can see, I am attending the meeting and giving my talk remotely. It's a great regret for me not to be present there in person. I understand that Corfu, although beautiful at all times of the year, is particularly so at this time. And I certainly hope to visit Corfu as well as the Corfu Institute in the future. Okay, so today I'd like to talk about some new results in SUN gauge matrix models. And in particular, I'd like to discuss the chiral anomaly that occurs and the extraction of light hadron masses from a particular SUN gauge matrix model, namely the SU3 gauge matrix model. Okay. This is joint work with Mohul Pandey, who is a postdoc currently at the Dublin Institute of Advanced Studies, and Nirmalendra Acharya, who is at the Indian Institute of Technology in Bhubaneswar. And the work I'm going to tell you about today is based on these two papers. One of them was published earlier this year, and the other one published last year. Okay, so I'll start off with the anomaly. And but before I do that, this is the outline of my talk. I'll briefly introduce the matrix model. I'll show you that there are instantons in this model. And when you couple fermions, then I will show you that there is a chiral anomaly. In particular, when you couple massless fermions, there is a chiral anomaly that develops. And I will discuss the implications of this of this particular result and of matrix model in general to low energy QCD. And I hope to end with maybe a discussion of where we can go from here. Okay, so let me briefly remind you what the chiral anomaly is. And before that, of course, we all know what an anomaly means. It's a symmetry of the classical theory, which cannot be implemented in the corresponding quantum theory. And perhaps the oldest and the best known example of this is the axial anomaly or the chiral anomaly. I will use these two names interchangeably. And this occurs in massless QCD. So as we know, massless QCD has two conserved U1s, classically, the U1 vector and the U1 axial, and they act on the quarks, like I've shown here. And this action by Noether's theorem in classical theory leads to these conserved currents. The vector current as well as the axial current is conserved. In quantum theory, one finds that the vector current continues to be conserved, but the axial current is anomalously broken. Axial current is, its divergence is no longer zero. That is, the U1 axial is anomalously broken. And in fact, the divergence of the axial current turns out to be proportional to F wedge F, where F is a gauge curvature. Okay. Now, the usual proofs for anomaly involve field theoretic techniques. So, for example, one might calculate the Feynman loop, one-loop Feynman diagrams, regulate the UV divergences, and study the change in the fermion path integral measure. So, this has led to sort of an folklore intuition that anomalies, if they occur, can happen only in field theories. That is, only in systems with an infinite number of degrees of freedom. What I will show you today is that this particular anomaly occurs in a quantum mechanical system, that is, in systems with finite number of degrees of freedom as well. And this will have implications for models of low energy QCD. Now, the strategy that I will use for showing this is almost the same as what we do in QFT. So we'll start off with the Euclidean formulation, and I'll show you, we'll see that the SUN Yang-Mills matrix model has self-dual and anti-self-dual instantons. These instantons can be given a topological charge. When you put quarks, then quarks develop normalizable zero modes in the background of the instanton. And this is, I guess, one of the most interesting parts, although personally I feel that all parts are interesting, that the zero mode contribution to the fermionic path integral turns out to be not invariant under axial transformations. So the axial charge or the chiral charge is thus not conserved. And this happens for all SUN, SU2, SU3, and all the way to SUN for n large, however large you want. Of course, there are going to be important differences compared to the QFT case, which I will point out along the way. And I will also show you that we discover a version of the index theorem as applicable to the matrix model. Okay, so let me start off by describing the matrix model for you. The building blocks are very simple. I start with 3 n by n Hermitian matrices. And the space of 3 n by n Hermitian matrices can be organized into, if you like, a single rectangular matrix 3 times n squared minus 1 sized matrix with real entries. Now, on this space of 3 n by n matrices, rotations act by left multiplication, while gauge transformations act via the adjoint action. Because these are gauge transformations, we need to quotient the configurations by space by these gauge transformations. So this is what my configuration space is defined to be. It's a quotient of m by add SUN. And we want this action to be, action of the add SUN to be free. And that leads to the configuration space that leads it to have rather complicated topology. Even something for as simple as SU2, the topology of the configuration space is like what I've shown here. We can also compute the curvature of the the Fij for this particular matrix model. It was first done by Narasimhan and Ramadas in 1979. In fact, they were also the ones who identified the topology of C2. And although I don't have time to show this here, you can show that this particular construction of the matrix model is a very natural reduction of SUN Yang-Mills theory on S3 cross R. Okay. So much so for the configuration space or the kinematics. What about dynamics? For that, we need a gauge invariant Lagrangian. The electric field is just the time derivative of M, and the magnetic field is the dual of the Fij that I wrote earlier. Of course, the electric field, when I say the time derivative of M, in order to make sure that there is a good covariance property under time-dependent gauge transformations, I have to add a parallel transporter, M0. So that's what the electric field looks like. And this is it, if you like. The matrix model is just half trace of, the Lagrangian is simply half trace of E squared minus B squared. This is our favorite Lagrangian. This is the Lagrangian for QCD or any Yang-Mills theory, if you like. And I've written out trace of BI as V because in this model, you can think of this V as a potential for a particle moving in some multi-dimensional space. And because V is the square of B, it has terms up to quartic, and therefore the matrix model is nothing but a multi-dimensional quartic oscillator. So let's look for instantons in this business. So we'll start off with the Euclidean action. It's the square of the Euclidean electric field plus the magnetic field. And you can see that the potential, which is B times B, trace of B times B, is always non-negative. So therefore, it's minimum whenever the M's obey this condition that I've written out here. The commutator of Mi with Mj is I epsilon ij k and k. And therefore, the minima of the potential are located whenever the M's are generators of n-dimensional representations of SU2. Of course, these generators, these J's, need not be reducible. And in fact, they could be composed of a bunch of irreducible representations. And let's say that there are not irreducible representations that make up the J's, make up the M. Okay. Now, this the action that I wrote out, because there are many minima, we can ask for solutions that connect these minima. In other words, we look for instantons. So in fact, there are both self-dual and anti-self-dual instantons, and they are solutions of this equation. It's basically the equation E equal to plus or minus B written out in the temporal gauge. And these instantons tunnel between two vacua, one labeled by J2 and the other labeled by J1. And if you want to just look at self-dual or anti-self-dual instantons, then we require that the two J's, J2 and J1, they commute. So it's very easy to write down the instanton solution. It's this function phi of tau times J1 plus 1 minus phi of tau times J2, where phi is this function that I've written down. If it's a self-dual instanton, then it is of the first form. If it's an anti-self-dual instanton, then it's of the second form. Now, for these instantons, for the self-dual instantons, I can define an instanton number. And this instanton number, I will define as the difference between the number of irreducible representations at either ends of tau. So R2 is the number of irreducible representations at the end J2, and R1 is the number of irreducible representations at the end J1. One is at tau equal to plus infinity, and the other is at tau equal to minus infinity. Okay. Now, this instanton number, now in usual continuum quantum field theory, well, continuum field theory, we can get the instanton number as the integral of a total derivative. Here too, it's possible to get the instanton number as the integral of a total tau derivative, and but it involves a particular rescaling of the electric field, of the Euclidean electric field. And what is nice about this instanton number is that it's a topological invariant in the sense that if you change your profile somewhere in the middle, but keep the ends fixed, then tau the matrix model instanton number does not change. So therefore, we can think of it as a topological invariant. Right. So much for the pure Yang-Mills part. Let's add in the fermions. They are very easy to add in. They are just Grassmann variables that depend only on time. And this is my fermionic action. The Dirac operator is again very straightforward to write down. I've again written it down in the temporal gauge. There's no problem putting the A0 back in. This D/ is Hermitian and commutes with gamma 5. So you can look for its eigenvalues and eigenfunctions, and the non-zero ones come in pairs. If lambda is the eigenvalue of psi, then minus lambda is the eigenvalue of gamma phi psi. So this is for the non-zero ones. For there are in fact also non-trivial zero modes. So there are a bunch of them. There can be a bunch of them. There could be n plus zero modes of positive chirality and n minus zero modes of negative chirality. And the difference between the number of zero modes, n plus minus n minus, is as we always do, we define as the index of the Dirac operator. Okay. So now these phis and chi's together, they form a complete set. And we can look at the Dirac operator in, say, the self-dual or the anti-self-dual instanton background. And it's a very straightforward application of the Kalya's index theorem, which we adapt to our case. And it tells us that the index of the Dirac operator for the self-dual background is minus the index for the anti-self-dual background. And amazingly enough, it is just the difference R2 minus R1. It's exactly the difference between the number of irreps at the two ends. So this is, if you like, the matrix model version of the index theorem, that the index of D/, which is the number of difference between the number of plus and minus chirality modes, is equal to R2 minus R1. Now notice that the tau is a quantity that is computed in the pure gauge sector, whereas the index is computed as the difference between the number of zero modes of opposite chiralities. So it's a remarkable, it is a remarkable fact that there exists such a simple relationship between these two quantities. Okay. And finally, the anomaly, again, it's a very straightforward matter to compute. You look at what happens to the fermion measure under a global chiral transformation, a global axial transformation, and you find that this is how the measure changes. The measure d mu changes by this factor, which has curly A in it. And this sum here is, of course, sum over all n's. So it's potentially a divergent sum. So we regularize A, as was taught to us long time ago by Fujikawa. And with a little bit of work, you can show that only zero modes contribute to this. So if you, at the end of the day, this contribution to the integral of A over d tau is simply the number of positive positive chirality zero modes minus the number of negative chirality zero modes. So this is our integrated anomaly. So that's it. If you like, you can see that because the fermion measure is not invariant, it means that chiral symmetry cannot be implemented and therefore it's broken. Of course, this chiral transformation was by a finite angle alpha. So if you choose alpha judiciously, then this anomaly term vanishes. So if you, in particular, if you choose alpha to be n pi, then the A is actually 0. There are no zero modes. And the residual chiral symmetry is not fully broken, but there's a residual Z2 symmetry. You can do this whole exercise for NF flavors of fermions, and you find that the residual symmetry is Z2NF. The story for the adjoint fermions coupled to Yang-Mills is conceptually the same. It's different in some detail. These coupling adjoint fermions to the matrix model is an interesting question because SUSY gauge matrix models have adjoint fermions in them. Here again, the way to go about in hunting for the anomaly is to embed the instanton in the adjoint representation. And again, we find that chiral symmetry is broken. I will not go over the details because the details go over the derivation because the derivation is more or less the same. But the index now is given by the difference, the index, which is the difference between the number of zero modes, is now related to the instanton number, but now in the adjoint representation. That is different from the instanton number in the fundamental representation. If you have a single Weil fermion, then in this case, the axial anomaly is broken to Z4, whereas if you have NF flavors, the residual symmetry is now Z of 4NF. Okay, so why, I mean, one might think that this is a somewhat specialized discussion, and you can ask whether this has any implications for the real world. And the first question that one might face is that the matrix model is, after all, a dramatic truncation of full Yang-Mills quantum field theory. The full field theory has been truncated to quantum mechanics. So are there any quantitative predictions that the matrix model has for reality? And I will show you that the answer is indeed yes. So for that, let's look at the SU3 matrix model, which is coupled to 3 flavors of quarks, U, D, and S. So this is, if you like, as close as you can get to Yang-Mills theory, to QCD actually, as close you can get to QCD. Now, you can find the energies of the matrix model has a Hamiltonian, so therefore you can compute its energies. And these energies, I have now put back the radius of S3, which is capital R, the Yang-Mills coupling G, and then the bare quark masses mu/d, which I have taken to be the same, and m strange. So I've taken U and D quark masses to be the same, and the strange quark mass to be a different mass. And we can find the E's using variational methods. What we found is that if you look at the differences, if you look at the ratios of energy differences, then they do not depend on R anymore. They only depend on G and the quark masses. And more remarkably, these ratios tend to finite limits in strong coupling. For G going to infinity, these ratios tend to finite limits. So then once we recognize this, it was an easy, conceptually at least, it was an easy step to make connection to making predictions for masses, we take four of these ratios and fix these ratios to be to the masses or to the masses of 4 physical particles. So you compute the mass differences for these 4 physical particles and fix these ratios to that. This gives us the RG flow equations, well, actually the integrated RG equation for how R flows as a function of G and how the quark masses flow as a function of G. And once we have these functions, we can use these functions to predict the masses of the other hadrons that we have. So this is what we found. The blue dots are the dots that we have taken from the particle data book, and the black dot along with the error bar is the prediction of the matrix model. I will show you, if there is time, I will show you numerical values for this. But even if you just cursory look at this table, tells you that apart from the K meson, the eta and the eta prime, where we are quite off, for all the other particles, we are doing quite well. So in the table of predictions, obviously the pi, the rho, the lambda, and delta are not there because those are the 4 particles that we've used as our inputs. And these remaining particles that you see here are the predictions of the matrix model. So this brings us to the question, if you like, to me at least to my mind, the importance of studying matrix models from the point of view that I presented. And in particular, it behooves on us to try to improve our conceptual understanding of this model. And specifically, when coupled to massless quarks, NF flavors, you can ask, is there a chiral anomaly? And we have just answered the question in affirmative. And more interestingly, is the SUNF left cross SUNF right, is it broken to SUNF diagonal? In other words, is there chiral symmetry breaking? And again, to that, the answer is yes. We are almost there, but we have a few I's to dot and T's to cross, so to speak. But so it looks like what we have is a new and a fairly good model for attacking the problem of the QCD masses, at least at extreme low energy or super strong coupling. So I'd like to summarize my talk here. I don't know how much time I have left.
2 minutes.
I have 2 minutes left. Okay, thank you. So this is a good time to summarize, to come to the summary. So what although I did not show you the matrix model that I described to you, the configuration space captures the non-trivial topological character of the full gauge bundle. This was first shown by Narasimhan and Ramdas many years ago in 1979. If you look at if you write down the Yang-Mills Lagrangian or the Yang-Mills action, then it admits instantons. Although unlike the full field theory case, there are only a finite number of distinct instantons. You can couple the Dirac fermion, and in the instanton background, the Dirac fermion has chiral zero modes, n plus of them with plus chirality and n minus with the opposite chirality. You find that there is an index theorem which tells you that the instanton number is equal to the Dirac index. And you can show that under a chiral transformation, the fermion measure is broken. It's not invariant. So therefore, chiral symmetry is anomalous for all n, even for n small, n equal to 2, n equal to 3, for every n every n you like, chiral symmetry is broken. So that was what I described to you earlier. Then towards the end, I showed you about how you can do variational estimates, and variational estimates give you excellent agreement with glue ball masses, which I did not have time to show you. And I showed you about the data on the matrix model prediction of the light hadron masses. And in particular, What this means is that the SU3 matrix model coupled to 3-flavor fermions, 3-flavor quarks, should be taken seriously as a model for extreme low energy QCD. I think that most of the studies of the matrix model focus on the large n limit. And I have tried to argue that the small n limit is interesting and useful. Thank you very much.
Thank you, Sachindeo. So, are there questions, comments? Yes, please.
Thank you for very interesting talk and agreement with Light Hadron mass. Is it possible to calculate something which is too hard in lattice QCD, but somehow you can really make use advantage of this simpler model?
So I have flashed my transparency, my slide with the where I have written out the masses, again, the observed mass and the particle and the matrix model prediction. So you can see that for a model that is so crude, we are doing quite well, except for the k, eta, and eta prime. And we think that we know that it is because our ansatz for the glue part in the variational calculation, our ansatz for the glue part was not big enough. So we are working on the bigger trial set where we hope to improve. And with the bigger trial set, we are optimistic that our predictions for k, eta, and eta prime will also improve. With regard to comparison with lattice, now you can see that I mean, lattice, of course, is an enormous enterprise, if you like, involving many supercomputers spread over many universities and has enormous amount of both computational as well as human manpower available. Here, as you can see, this entire calculation was done on a laptop, and it took a few weeks. And as far as manpower is concerned, it's 2 people who did this work. So I think that over time, this particular way of computing will give us a quick and quick, reliable, and fast way of estimating masses in regions of QCD like heavy quark physics, where I believe lattice computations struggle to make predictions.
You do believe that it can you may be able to have some advantage compared to lattice QCD calculation?
I wouldn't like to go that far, because as far as I know, the error bars that lattice people produce are much lower, much tighter. So we should be realistic about what the matrix model tells us. But for me, if you like, the takeaway message is that the modes that are the modes of QCD that the matrix model represent, if you like, these modes are responsible for anything between 75 to 99% of the mass of the light hadrons. The full field theory contributes very little to the mass of the light hadrons, except, I mean, we'll have to, when we have better data for k, eta prime, we will. But if you look at all the other particles, most of the mass of the light hadron comes from this particular mode of QCD. I did not, as far as I know, we personally, of course, did not know about this, but I also, from searching the literature, I have not found any statement to this effect that most of the mass comes from this mode. And contribution of field theory to the mass, the full field theory to the mass, is substantially smaller. So, I'm sorry, does that answer your question?
Yeah. So, is it okay to go another question, or maybe I should finish?
Yes, please. Thank you.
Let me check whether there is anybody on the online. No, I wanted to say, check whether there is anybody online, please.
Before.
Well, go ahead, go ahead.
Sorry, can you, is it something you can say about gluables?
Yes, here you go. This was calculation that we did. This was our first try at variational calculation, and so this is with the pure Yang-Mills matrix model, no quarks, and these are our predictions. Of course, glue balls are we can't. There is no particle data entry for reliable one for glue balls. So the only thing we can compare matrix model predictions are to the predictions that are produced from lattice. So that is my third column here. And again, you can see that except for a couple of them, I am doing quite well as far as, so these are glue balls. These are glue balls in the SU3 gauge theory. We didn't compute them for the SU2 or any other SU. So these are our predictions. Our understanding as well as our control on the problem was much poorer. This was work that we did about 3 years ago, I think. Does that help you to see these? Predictions for glue balls?
Yeah, I will look afterwards for the details. Thank you very much.
Okay, sure.
So, if there's no further question, let's have a last question by, you wanted to ask a last question, didn't you?
Just maybe relevant question. I just wondered if it's possible to go to larger N and compare it with the lattice result, if there is such lattice data, and you can check.
By larger N, you mean SU4, SU5, etc., right?
Some lattice.
Yeah. I know that there is a man called Tepper, I think, in England. And recently, along with collaborators, he has done work on glue ball predictions for higher SUs. So there is lattice data, I think, available for SUs other than 2 and 3. There is no obstruction in our formalism to do variational calculations for other SUs. And you can definitely do them. And we will be able to compare them with lattice predictions for SU4, SU5, etc. For me personally, the exciting part is to compare with things that are printed in the particle data book, because to me that is the ultimate test of whether the matrix model is good for anything at all. And I think that the matrix model passes that test quite well. And what is interesting and important, I think, is that it passes that test for low values of n. This slide that I'm showing you is for n equal to 3. And I think that the community, because of the influence of ADS CFT, has been looking very hard at n equal to infinity, and has missed out interesting things at low values of n. N equal to infinity is of course very interesting. There is no doubt about it. But I wanted to argue that n equal to 2 and 3 in particular, is also extremely interesting.
That I do agree, but I also thought that maybe like there is a possibility that at large N agreement becomes better and better. If such a thing, then it could give you some theoretical.
Yes, but if we do computations for SU5, SU10, SU100, there is no book, there is no experimentalist who will take us seriously. because we have nothing to compare it with.
Yeah, but agreement with the lattice calculator, but it's fine.
Yes, of course, yes. Agreement with lattice, yes. I agree.
Okay, so let's thank again Sachindeo, Vaidya, for this very clear talk.
Thank you very much.
Thank you, and we reconvene in 25 minutes. Sachindeo, I have actually a question.
Yes, please.
Not time to, because
Would you like to see my slides?
no, not necessary.
Okay.
I just had a comment about this glue ball calculation.
Okay. Right.
I think it might be interesting to have not only the precise calculation, but also estimate of possible further states. As far as I recall, in the ADS-CFT stringy community, there were foretelling further states that then were found by the lattice people. So I was wondering whether the matrix model could be used to figure out extra states.
It can certainly be used to attack the question. I can't guess as to what the predictions, what the results of the matrix model will be. But basically the point is you start off with this Hamiltonian, which is a multi-dimensional quartic oscillator, and just find the spectrum, find the energy eigenvalues variationally. And essentially you are limited by how much patience you have and how much computing power you have for all variational calculations. But the results that I showed you for glue balls were with a fairly small number of states. For the spin zero, we had order of 17 or 18 the size of the trial set was 17 or 18 states, and a similar number for spin 1 and spin 2, 16 and 20 or something like that. The hard and annoying part was to construct long chains of colorless states. So that was the, but yes, we can definitely try to, we can assess which can be used as for benchmarking lattice computations.
Thank you.
Okay. Thank you.
Uh, 4:30, 5:30. Yes. Yes. So there is one question, one point I would like to.